Good afternoon, everyone, and a very warm welcome to this webinar on geophysics and digital 3D modeling for safer tunnel design and construction. Thank you for taking the time to join us today. Before we begin, just a very few quick housekeeping notes. We request all participants to please post their questions in the chat box because these questions will be taken up at the end of the session. So we want you to post your queries in the chat box and these will be taken up in the Q&A session. Don't worry about it. The recording of today's session will be made available to all registered participants. A WhatsApp group link will be shared in the chat box as well. You may join this group to receive the recordings and all related updates to this webinar. This WhatsApp group link has been created and shared with you with all registered participants previously as well. If you haven't received it, don't worry, it will be shared again in the chat box. Now coming back to the webinar, tunneling is one of the most fascinating and challenging areas of infrastructure engineering. The biggest reason is very simple. We are building in ground that we cannot see. We cannot see fully. Even with boreholes and geological mapping, only a tiny fraction of the subsurface is actually investigated. Much of what lies between those 2 points is either assumed or interpreted, and that is where geological surprises may crop up. Today's webinar focuses on how advanced geophysical investigations and modern digital modeling tools can help reduce this uncertainty and support smarter, safer tunnel projects. We have 2 excellent speakers with us today. In the first part of the webinar, Dr. Sanjay Rana will discuss the role of engineering geophysics in tunnel investigations and how different geophysical methods can provide continuous insight into ground conditions during planning, design, and construction stages. Dr. Rana is a pioneer of engineering geophysics in India with more than 3 decades of experience and involvement in over 2,000 infrastructure projects worldwide. In the second part of the webinar, Ms. Meghna Rawat, engineering geologist and customer solution specialist for Leapfrog Works at Sequent, will show how geophysical and geotechnical data can be integrated into digital 3D ground models to support tunnel design and risk management. So with that, let us begin. It is my pleasure to invite Dr. Sanjay Rana to start the session. Dr. Rana, over to you.
So thank you, Suchetna, for that introduction and for setting the context so nicely. Before we begin, I would like to acknowledge the people who have worked behind the scenes to make this webinar possible. Mr. Rashid Katuria is the person behind setting up everything digitally, including Zoom platform and solving all your problems. Ms. Anushka Batra, she has been interacting with you on various social media platforms. Ms. Priya Mohini, first ever female geophysicist from the state of Jammu and Kashmir, and a big advocate of near surface geophysics and all the webinars which we conduct. Ms. Suchetna Banerjee, of course, and my fellow speaker, Ms. Meghna Rawat. So thank you for your efforts in bringing this session together. And thank you to all the participants who have taken time to join us today. We often call these sessions free webinars, but we actually never consider them free because you are contributing something extremely valuable, and that is your time. And we deeply respect that. So we will try our best to keep this session as informative, practical, and insight-packed as possible. Since time is limited, we might not be able to elaborate on all the concepts, but feel free to interact with us even after the webinar. As I say, it's always a start of the relationship. And once the webinar ends, it really doesn't end, a communication starts. So let me begin with a simple thought about tunneling. We are about to excavate millions of cubic meters of ground that we have barely seen. The success of a tunnel project depends not only on how well we excavate the ground, but how well we understand it before we start. In tunnel engineering, the biggest risk is not the rock, the machine, or the design. It is what we do not know about the ground below and ahead. And that is precisely where engineering geophysics becomes extremely valuable, because it helps us see beyond the boreholes and reduce the uncertainties that lie ahead of the tunnel face and below the surface. So with this starting, I'll now start sharing my screen and begin my presentation. So just allow me a moment to do that. And I'll keep checking everything in between with Rashik ji. So 1 minute. Right. So quick check, Rashik ji, my screen is visible
Yes, sir, it is.
and my voice is clear?
Yes.
Great. So let's start with the first part of the webinar. As we said, second part will be taken by Miss Meghna Rawat. First part is going to deal with geophysics. And very brief introduction about the company which I represent, that's Parson. Parson is a geophysical company. We are an ISO certified geophysical company. We are the largest in the region in the field of near surface. But more than that, we are known for bringing various innovations and technologies from time to time into the country. Is starting with bringing GPR in 96, then shear wave refraction in 97, high resolution tomography in 98, and the list goes on. I'm not going through the list. The latest, of course, has been BEAM, that is a special tunnel head monitoring technique, which we brought to India in 2022 and already has been used in multiple projects. Our strength, of course, is our experienced and trained people. We are an Indian multinational, so we have our head office in Delhi, and we have our offices in Singapore, Bahrain, and Saudi Arabia. And through these offices, we are catering to 14 countries around the world. I'm a geophysicist by profession. I graduated in 1990. That's around 36 years back from University of Roorkee, which is now IIT Roorkee. I started with my career with the state government, then went on to central government, that's Department of Atomic Energy. And 1995 is the time when I took the plunge and got into starting the first ever near surface geophysics company in the country. When geophysics was little known is an overstatement, not at all known. People really didn't understand the value of near surface geophysics or how it can be applied for various problems. Since then, I've been just doing that, nothing much. And I'm also a member of various working committees because standards and code of practices are very important for any technology. So I'm on 7 committees of Bureau of Indian Standard, that is BIS. I've developed code for IRC, Indian Road Congress, Tunneling Association of India, and INDSCT, that is Indian Society for Transist Technology. Here are a list of a few of the codes which have been authored by me. So with this small introduction, let's come right to the topic. So in very, very famous words of Sri Visvesvaraya, he said the engineer's first problem in any design situation is to discover what the problem really is. That is, if we can identify what problem we are dealing with, half the problem is solved. Very much like life in general. In life also, sometimes we come across a problem, we are very depressed about it. But if we are able to self-contemplate, if we are able to look at the problem and understand where the problem is coming from, more often than not, we are able to solve the problem. And same applies to engineering also. So this passage basically says we should be able to define the problem, we should be able to investigate properly, and we must avoid assumptions. That is what engineering is all about. That brings me to a quiz to start the session. It's very important that we take this quiz very seriously. So my request to you that take this quiz very seriously. So here it is. Let's say we know our Earth. I think it has a radius of around 6,400 kilometers. So if we wrap a rope around the Earth, right, we are wrapping a rope around the Earth. And now we take this rope, and I'm a Superman, so I can actually go around the Earth and wrap the rope. And then I take this rope away and just increase it by 1 meter in length. And now again I go around the Earth. How far above the Earth's surface will the rope be? So that's the question for you. I hope you understand the question. All right. So I'll just make it. So this is the rope which I wrapped around the Earth. Now I opened this rope and took it out and just added a 6 meter to it, just a 6 meter. Okay. And then again I went around the Earth and wrapped it. Now, how far above this will go from the Earth's surface? That's the question. Simple question. And your options are A is negligible, B is 1 mm, C is 10 mm, and D is 1 meter. And I would love to have your answers in the chat box now. Please, let's have quick answers in the chat box. Let's do it. Let me see your answers. A, B, C, or D. In the chat box, please. A. Too many A's. Negligible, A, negligible, A, negligible, A, negligible, A. Wonderful. All right. Negligible, A, negligible, A. Makes a lot of sense, actually. Negligible. Please do not do annotation on the screen. Please do not do that, okay? Kindly do not do that. All right, so great. So they're all A's. Wonderful. And few negligibles. Great. Makes sense, actually. Makes sense. Makes common sense. Because what I requested before asking this question was that we should try not to assume. All right. And please do not, Rashikji, can we stop this sketching on the screen? I'll stop sharing my screen. And just let's erase this sketching on the screen and stop this, disable this feature, please.
I've done that in the backend now. Start sharing again, please.
Yeah, so I'll start sharing again. Okay. All right. So this was a question and the answer we have seen. Now, a quick calculation. R dash is no new radius. So 2 pi r dash, that is a circumference. 2 pi r dash is 2 pi r plus 6. R dash minus r is 6 upon 2 pi, that is 0.955 meters, that is 1 meter. The rope will be 1 meter above the Earth's surface. Unbelievable, right? Only answer was negligible and 0.1 mm because we were just assuming. And what we were told just before this question, always measure or calculate, don't assume or guess. So keep this question in your mind always after this webinar, that whenever we are dealing even with the simplest problem, as engineers, we are supposed to calculate and measure, not assume and guess. Unfortunately, that's what we are doing in engineering world all the time. That is, be it a tunneling project or any infrastructure project, we are depending heavily only on drilling, and between the boreholes, it's all guesswork. It's all interpolation, it's all assumption, it's all guesswork. There's no measurement there. But we are depending on this heavily, and that's all we are doing all the time. So when we talk about investigation, investigation can be defined as a methodology of acquiring advanced knowledge of the site conditions so that a techno-commercially viable project layout can be developed. That is what is investigation. So we want to find out the advanced knowledge of the site conditions so that we can do a good techno-commercially viable project. It also has been proven around the world, not only in India, that quality of investigation, quantity of investigation, and time allowed for investigation means less uncertainties and less cost and claims. Take any project across the world, look at how much money has been spent on investigation, compare that with the cost overrun, and you will always find they are inversely proportional. That is, more money you are spending on investigation, lesser are your costs and claims and delays, etc., etc. And this is a very good statistics, challenges of underground. It is from ITA, International Tunneling Association. So these statistics I have not made up. So this says even a comprehensive exploration program recovers a relatively minuscule drill core volume that is less than 0.0005% of future excavated volume of the tunnel. And there is a basis of this sampling level, 100-meter diameter borehole up to 100 meters in a 5-meter diameter tunnel, etc., etc. But look at the number here, 0.0005%. So that is the amount of information we are actually collecting for designing our project. And that too, when we talk of comprehensive exploration program, that is, we are spending some 5 to 7% or at least 5% of the project cost on investigation. In fact, in India, most of the projects we are spending around 0.75%, invariably less than 1% on investigation. So actually, you can add one more zero into this uncertainty. With this information, we make our DPRs, we make our plans, we do everything. So can we call ourselves a decision maker, a smart decision makers when we are doing things with practically our eyes closed? I'm sure answer is absolutely no. And then we come across what we call geological surprises. That is, we were doing tunneling, suddenly we came across aquifer zone. We were doing tunneling, there was shear zone, etc., etc. So the point is that expertise and engineering solution is available for dealing with almost any ground condition. That is, you know that you're going to come across a shear zone, you can pre-grout it and go ahead with your tunneling. Whatever is the ground condition, there is an engineering solution to deal with that, provided you know about the expected presence of this particular zone. So the problem is meeting the unexpected and uncertainty of the ground condition. So the next question is, all right, enough lecture. So how much investigation should we be doing? Can we drill every 1 meter along the tunnel route? Shall we convert the ground into Swiss cheese? And the answer is no. Obviously, you cannot do that. That's not technically feasible. That's not commercially viable. Absolutely not possible. And then comes the question, what can we do? And that's where geophysical investigation comes in picture. For the uninitiated, although many of you have seen the list of registered participants, and for this webinar, by the way, we have 1,070 registrations when I started this webinar. Although less than 300 have joined, but that's generally every time the case. Many of you go through the recordings later, which is a perfectly good way of doing it. So many of you are experienced. I've seen your designations and organizations, but for the uninitiated, students especially, when I define geophysical investigation, I love to compare it with medical science. So in medical science, you have X-ray, ultrasound, MRI, CT scan. What are we doing here? We are sending different kind of rays and waves inside the human body to create an image of what's inside. Same thing we are doing in geophysics. That is, we are sending different kind of rays and waves inside the earth, or measuring the naturally occurring fields like gravitational field or magnetic field or telluric field, trying to create an image of what's inside the earth. So that is a very, very good analogy to understand what geophysics is. So geophysics does the same with the earth, which a medical imaging professional does with the human body. Simple. So why use it? So this analogy makes it very easy to answer this question. Why use it? If you have a problem, like let's say you have a pain in the abdomen and you go to the clinic, would you like to be cut open, or would you like to go for ultrasound first and then at all cut open if it is needed? Right? So that's where the answer is, why use geophysics? First of all, it's low cost. Compared to any invasive method, geophysics is a very, very cheap method. Rapid coverage. You can cover hundreds of and thousands of kilometers in a day, especially with the heliborne and airborne techniques which are available today. It gives you continuous information. That's the biggest point. Drilling gives you discrete information. Look at this diagram here. So is a void here, there's a limestone pinnacle, and there are few anthropological features. If you're only depending on drilling, the chances that you will detect any of these isolated features is 1 in 1,000 or 1 in million, depending on what is the spacing between your drill holes and what is the size of these objects. Whereas if you do a good geophysical campaign, you will detect and map all these anomalies irrespective of their size. All right. That is why it's so important to have continuous information. And then next is optimization of drill hole. Geophysics does not replace drilling. Very, very important message to understand. It complements, does not replace. Geophysics is not equal to geotechnics. They measure different things. When you integrate them, it enhances interpretation, reduces uncertainties, and guides smarter and targeted drilling. Okay, so optimization of drill holes. If your tunnel is 10 kilometers, and you decide I'm going to drill every 100 meter, right? That's not a great thing to do, because you're going to do a lot of drilling and it's still things which are happening between these 100 meters you will not be able to detect, right? So geophysics gives you continuous information, and then you can target your drilling in the anomalies where you need more information, which ultimately, once you have continuous information, leads to minimization of surprises. And it's always good for early stage application. I have been working in this field for 36 years, in near surface geophysics for 31 years. Still, most of the calls I get are firefighting calls. Something wrong has happened and now they want us. That's not the way. You do not conduct ultrasound after the surgery has failed to locate the problem. You conduct ultrasound before you go for the surgery, right? So that's the sequence. So when we talk of tunnel or underground project site investigation, what is the right sequence? So right sequence, of course, it starts with the available geological maps, satellite images, geological mapping. Undoubtedly, these are the starting points of the whole campaign. Then geophysical investigations, always invariably before drilling. Always invariably before drilling, not with drilling, not after drilling. Even today, a lot of tenders are coming or come where geophysical investigation and drilling are being put in the same tender, and both are done simultaneously. You are losing the value of geophysics in the process. You should first carry out a geophysical investigation, identify the areas where drilling needs to be done, and then do the drilling. So geophysical investigation, then drilling, then other hydrogeological studies, seismicity studies, etc., etc. That's the right sequence. So it doesn't live in isolation. It is all integrated. So geotechnical methods tell us what exactly is there, because they're very, very accurate. But they tell you only where you test. That is only at that point where you do the drilling. Geophysics is something which gives you continuous information, fills all the gaps, provides a broader picture, and you are able to target your boreholes more effectively. So together, they make a great combination. And ultimately, with this, you can avoid surprises during construction. Avoid surprises basically means less cost overruns, less time overruns, etc. I have divided discussion on the methods in three parts. Okay, I'm not going to discuss in great details about all the methods because time is limited for the webinar. One is a planning stage, something which you are doing at the level of planning. Then is the execution stage, and third is the QC stage, the quality control stage, right? So planning stage. Let's start with the planning stage. You want to make a tunnel from point A to point B. All right. You want to connect, let's say, Delhi to or Rishikesh to Kedarnath, whatever. You're connecting two places through a tunnel. First method I'm going to discuss is heliborne time domain electromagnetic. It's a very, very strong method in the initial planning stage. So you have, let's say, different alignments are possible. Today, this decision we take generally with the topo sheets, some geological maps which are available. That is how we take this decision, right? So 1, 2, 3, three alignments are there, which one to go for. So there comes this heliborne geoscanning, in which this is the helicopter. This is a loop suspended from the helicopter. This is flown over the ground. It is obviously electromagnetic induction is the basic principle on this. I'm not going in details. No boring stuff in this webinar. Ultimately, what you get is a 2D or 3D conductivity map of the subsurface up to a depth of 600 to 800 meters, depending on various factors, including conductivity of the ground and if there is any conductive layer in between. But that's generally the range, 600 to 800 meters. You get a conductivity distribution in that particular area. How is the conductivity distribution important? Because rocks and dry soils are not conductive. Our features like shear zones, water lenses, etc. are highly conductive. So once you're able to have conductivity distribution, it gives you where the problem areas might be along your alignment. So you take a strip of, let's say you want to connect point A to point B. So you're not just investigating point A to point B. You take a strip 10 kilometers by, let's say, 500 meters. And you run a complete heliborne survey on this. make a 3D cube of the subsurface, and now you can choose what's the right alignment for your tunnel. Examples will be coming. Advantage, you can do it in steep terrains. So Himalayas, for example, right? You have dense vegetation. A geologist cannot even walk there. No one can walk there. There is no geological features visible because it's all thick vegetation. So mostly what we are doing is we are doing whatever geological study we can do on the nalas and whatever exposures are there along the road, etc., etc. Don't need to do that. Heliborne can be done in steep terrain, can be done in dense forest, snow cover, water, private land, everywhere. Reserve forest areas, because you're not putting your foot on the ground anyway. Limitations are there, coupling to infrastructure. So power lines, major roads, habitat areas. Flight is affected by weather, so heavy wind and fog will have limitations, but generally a very, very good method for quick study. And the tech behind is you have geological data, you have geotechnical data. If what you have from the drilling, whatever drilling is available, you have geophysical data. And now you put all this and you train your system through the approach of machine learning, create a model. This is the geo model ultimately, which we call it. Okay, it's not a geophysical model, it's not a geological model. It goes to the end user, and again, more data which is coming, that model will keep getting enhanced with more data input. So crafting simple ground models rapidly through ML to decrease geological risk. That is the tech behind what is being done now. So this is integrated and dynamic ground model, as we say, drilling. So once you have drilling data, as you can see, only at the point it is available, information is available, rest everything is interpolated in between. So this is a geotechnical data. Now you have geophysical data. So everything is there in geophysical data, but in terms of that particular parameter which you are measuring, it can be resistivity, it can be seismic velocity, whatever it is. So this is geophysical data, combine the two. This plus this, and now you have what we call a geo model. That is model in terms of geology, but not interpolated, coming from geophysical, all the in-between information, controlled by drilling the geological part of it. So geophysical data converted to geological data, ultimately coming as a geo model. So this is and more drilling data coming in, again it will more drilling data come, again it will be fed, and the model will be updated. So it is not a static model, it's a dynamic model. More and more data comes, that it is getting updated from time to time. So this is assumed geology of the area. And once survey was done, you can see what a contrast in geology is there. So this is scanned geology. So a lot of value in this. Similarly, this was an alignment which was almost finalized. Once the survey was done, it was very clear that alignment is passing through this zone, weakness zone, soft clays, and ultimately this alignment was discarded. Otherwise, this would have been a disaster if construction would have started there. This is a very interesting case study where alignment was there, and then scanning has been done. And once the scanning was done, it was clear that proposed alignment is passing above the rock cover in a substantial part of the area. Slightly shifted, alignment was slightly shifted based on the study, and that's it. It solved the problem. And the client finally says that thanks to this, we avoided $25 million in cost increase. So that is the kind of value addition these simple investigations can do in our tunneling projects. Second very good method in the initial stage is passive seismic tomography. So passive seismic, as the name indicates, is a passive method. So we are putting sensors on the top, on the ground. These are 3 component sensors. We are listening to micro earthquakes which are coming in under the earth all the time. And based on that, we are making VP, that is P wave velocity, and VP upon VS, that's closely related to Poisson's ratio. 3D map of the subsurface up to a depth of, in oil industry, we are doing up to a depth of 12 to 14 kilometers. In tunnel, again, it can be any depth which is desirable. So even if 2-kilometer overburden is there, it can be 2 kilometer. I'll just show you an example of, I think, 2.4 kilometers. So depth is not a problem in this case. So this is the way it is done. So this is a tunnel route. So a close sensor spacing along the tunnel route. Few sensors have been put around this also to capture the teleseismic events. These are the one. This was the exact tunnel route. So a lot of sensors along the tunnel route. So seismic interferometry can be done there. Few sensors around it. So the entire 3D model can be developed. As I said, 500 meters by let's say 10 kilometers, what we want to investigate. And this is just a section. This is a section how it comes. And let's say alignment was proposed at 0.4 meter, 0.4. So this is 2.4 kilometers here to here, the depth of investigation. Let's say it was planned here. So if you go like this, we are going in good strata. But as soon as you come here, you are entering very, very low velocity medium problem, right? So this tells you where you can get surprises if you start tunneling in this area. So these are initial methods which are very, very strong in having a quick review of the entire area. Then you have seismic refraction tomography, which is based on the principle of seismic refraction. I'm not going in details of that, but gives you very good information about the P-wave velocity distribution, which is directly linked to the strength of the medium. So this is one example in which this section was created based on available geological information. So, from here to here, this was all supposed to be good rock. This was a tunnel alignment which was there. And once investigation was done, you can see the weak zone here. You can see a weak zone here, and you can see a weak zone here, right? Other than these zones which were already there in the geological mapping, but these weak zones are very much here. And if these were not detected using this method, at the time of construction, they would have come as geological surprise. So geological surprise is nothing but a situation which has not been anticipated because you have not done your investigation properly. Okay, so this is the strength of seismic refraction tomography. It can detect small shear zones. So this is just a 7 to 10 meters wide shear zone which has been detected using this. Okay. And I requested not to please do annotations on the screen. Can we please stop that? Thank you. Next method is electrical resistivity imaging on tomography. So seismic refraction tomography is giving you P-wave velocity. That tells you about the strength of the formation. Seismic electrical resistivity imaging is giving you, again, resistivity or conductivity. This is a ground method, okay? So here we are putting electrodes along the ground. Sorry, before I go to that. Seismic refraction method, which we talked about, generally the depth without explosive is limited to 70, 80 meters, not more than that. If you use explosive, you can go even deeper, all right? Now, how deep? Well, Russians use seismic refraction to go up to Mohov. That's 29 kilometers. So actually, there is no limit, but generally 100 to 200 meters is what we keep seismic refraction limited to. Electrical resistivity imaging is, again, you put electrode along the alignment, and then you pump current, and what you get is a 2D or 3D model of the subsurface in terms of resistivity. So wherever you have good rock, you will have high resistivity. Wherever you have weak rock or shear zones or water bearing zones, you'll have low resistivity. So this was a shear zone in a tunneling project in the state of J&K. Here you can see this is 1060, this is 860. So you have 200 meters from here to here. You can investigate up to 300 meters easily using ERI. So this was a shear zone which was detected using this ERI, electrical resistivity imaging. And this is a beautiful example of how to target your drilling based on results of geophysics. So you can see this is 1500 meter chainage to 2500 meter chainage. So this is the tunnel, and this is a tunnel route proposed. Electrical resistivity imaging has been done. And now you see here, one low resistivity zone has been detected here. One low resistivity zone has been detected here. Based on this information, one drill hole has been proposed here and one drill hole has been proposed here. No drilling every 50 meters, every 100 meters, every 500 meters, right? Targeted drilling in the anomalies to now investigate these further. Beautiful example of how to target your drilling based on geophysics. You can also create 3D model of the entire thing. So this is a 3D model, and this is not something which I did yesterday. This is something which I think I did in 2001 or 2002, long time back. So this is 60 meters wide, 60-meter deep and 300-meter long cube. This is all water table. This was done to detect a cavity in sandstone, otherwise good sandstone. And once we cut this slice from the other side, you will see this is the cavity which is traveling like this. It was like a tubular cavity from one end to the other. So this is the cavity. So you can convert your and obviously Meghna will be talking more about all this, how to use your software for this data. Then you have shear wave velocity models, because P wave velocity is giving you compressional strength, compressive strength. Then you need shear strength also. So REMI and MASW are method for shear strength, which are based on Rayleigh wave dispersion curve. And this is a result of MASW. So you can see this is the weak zone, low velocity zone, which has been detected. This is a tunnel project. This is a built up tunnel. There was some subsidence taking place on the top, and it was desired to know where it is taking place from so that the area can be treated. And these zones were detected. Number of zones. I've just kept one or two examples in this presentation. This is refraction microtremor. Again, you can see this is a bedrock at 80 meters depth, and these are the low velocity zones on these areas. Then seismic tomography, a very, very strong method. And I would like you to pay special attention to this, because whatever surface methods we are doing, as we keep going down, the resolution will become lesser and lesser. Now, sometimes we need very high resolution information at great depths. Seismic tomography does that. So it is done between two boreholes or between two faces. So we send number of these seismic waves across the boreholes or faces, and then we do the inversion, and you have a continuous high resolution image between the boreholes. So here, this is drill hole, 5 drill holes. Tomography has been done between them, and now there is no interpolation between the drill holes. Continuous information, and this fault has been detected based on the tomography which has been done here. So this is a very, very high resolution method to get information, continuous information between drill holes. This is the deepest seismic tomography reported in the world to the best of my knowledge. We are very proud of this project. This was done in Bhutan by us. And drill hole were drilled up to a depth of 350 meters. So you can see here it is 235 meters, I think. And at one point, distance between borehole was as high as 115 meters. So these are the cavities which were to be detected. And this is the beautiful definition of cavities. And at one point, cavity was as big as 85 meters by 60 meters, and distance here between borehole is as much as 115 meters. Okay, so this is a very strong method to get high resolution information even in the deeper areas. And those of you who have tuned from metro, this is a great solution for you for your metro projects. Sometimes your metro alignment is going under the buildings. You cannot do anything there. You cannot do drilling there. You cannot do surface geophysics there. But there is a road in the front and there is a road in the rear, which can be a service lane, etc., etc. If you're able to put 2 drill holes on these roads on either side of your building and do your seismic tomography between them, once you process the entire thing, now you have all the information right under your building where your tunnel alignment is passing through. So this is a solution for people, especially who are working on metro tunnels. You can also, this is a project which we did recently. There were twin tunnels for metro, and they knew that there is few voids which have developed between these tunnels. So these are tomography which has been done between the tunnels. So this is one this receiver source like this. 4 planes have been done between these twin tunnels. And once you process the data, you are able to see the weak zones between these tunnels so clearly. Here, the weak zones between the tunnels so clearly. Now you know exactly where to do the treatment, so your entire ground is remaining stable even when the operations get started. Very strong method. Seismic reflection is something which is used in oil and gas industry a lot, and can be used for tunnel route investigation also, because it can go up to even 4 to 6 kilometers down. But the logistics are a problem, so I'll not spend much time on this because logistically it is slightly challenging. You have to do drilling practically every 10 meters up to a depth of around 10 meters to put the explosives there, etc., etc. But it is being used in other countries. There are few examples of its use from Canada. But anyone interested, we can talk about it. I just included it here, but slightly difficult. Other methods are MT, magnetotelluric, GPR, etc. Then comes execution stage when you are actually doing the tunnel execution. Now you want to see ahead of the phase because you have done your geophysics, you have beautifully tried to map the ground, but as you are executing, you can even get more high resolution data which might have got missed by surface geophysics, right? There comes methods like tunnel seismic prediction. So this was an excellent example of what I was talking about. TSP is based on principle of seismic reflection. So if there any weak zone, you'll be able to detect it based on seismic reflection. Acoustic impedance. Acoustic impedance is velocity multiplied by density. So you're able to detect the weak zone and then pre-consolidation before you go through that zone. So it's no more a surprise, right? And then this is based on seismic reflection. Then there is another method that's beam. It's an electrical method. It is based on conductivity. There are many clients who come to me and say, shall we get TSP done or shall we get beam done? See, there is no either and or in geophysics. It's all about combining tools. TSP is great. It has its certain limitations in terms of the inclination of this weak zone, right? It is working on seismic property. It is not working on the property of presence of water, moisture. Now, if you are interested in understanding the presence of water, you are going for an electrical method along with a seismic method, which is detecting the strength of the material there, right? So there is no either or. It's about combining methods. Beam is a very strong method, which is based on electrical. We call it bore tunneling electrical ahead monitoring. In this, you don't need to stop your tunneling operation even for a moment, right? It is a continuous method. So stroke by stroke, as the tunneling is happening, you're getting the data from there. It's totally non-invasive, automatic, continuous, non-invasive data acquisition, processing, evaluation, interpretation, and documentation in real time without any hindrance in your TBM operation. Here, what we do, we use 3 electrodes. One electrode is put behind the rotating head on the static part. One electrode is put on the shield, and one electrode, third electrode, goes outside in the neutral ground. No theory, as I promised. At the end of it, what you get? Focus zone is 3 times the tunnel diameter. So if your tunnel diameter is 6.67, around 20 meters ahead, you will keep getting the information on what is coming there. If there's a cavity coming there, if there is a aquifer coming ahead of you, etc., etc. Continuous information. And this information is seen in the steering cabin of the TBM, is transmitted in the real time to the engineering office, to the head office, to any office around the world. You can transmit it, okay? So people can take decision. 3 times the tunnel diameter is the zone from which you get the information. So this is a very strong method for TBM tunnelings. Then other applicable methods, of course, GPR is there. I'm not discussing it right now. Anyone interested can really contact me. Last part is QC and maintenance stage. Tunnel has been built, but whether it is all in good condition, there you have things like GPR, which you can use in your built-up tunnel to see if there is any cavity or void behind your tunnel lining. This is an example of recently a tunnel project which we did. So this is a traffic tunnel. Traffic is very much flowing here. And this is a GPR antenna which we are taking all along the tunnel line at different elevations. And ultimately, using this data, we'll create a 3D model of the tunnel. See again here at different level, I said, this is a higher level, this is a lower level, this is even a lower level. Like this, we'll cover the entire tunnel. And at the end of it, we'll create a model like this. So wherever you have any problems in the, so this is the tunnel, and this is ground beyond the tunnel. Wherever you have any problem in terms of cavities or delamination, you will have your red hotspots, as we call it, high reflections, and you'll be able to get it. You can again cut it in slices at different changes, see how the zone is going from one part to the other. Very strong method, simple GPR, based different frequencies, but you can model the entire tunnel in 3 dimensions. Here you see, this is a zone, which is a problematic zone. Once you know about this zone, where it is, you can treat it. As simple as that. Again, if you just open this tunnel like this, here these red ones are the areas which are basically cavities which have developed. You know the chainage, where the cavity is there. You know in X and Y and Z, 65 to 72 centimeters, 72 to 79 centimeter. So from where the cavity has started up to where the cavity is going. Second method which can be used very effectively for tunnels is electrical resistivity imaging. So let's say you have a seepage coming from some point and you want to stop the seepage. To stopping the seepage, you should know where it is coming from. Now, generally, we assume it is coming from where we are able to see it and we start grouting there. Well, unfortunately, that's not the case all the time. So we put our electrodes on the tunnel, and once you do this, seepage was coming from this point. And when ERI was done, it was seen that this is a saturation zone where water saturation had taken place and seepage was taking this path. So if you start grouting here, you will not be able to grout anything because this is a very, very highly resistive medium. This is the area which is to be treated. So that's how ERI becomes very valuable in this. Limitations and reasons of failure, I think second last slide of my presentation. First is inadequate planning and survey design. Geophysics, again, is like medical science. If you have broken bone, you can go for X-ray. If you have tissue issues, you have to go for MRI. If you have to scan this in high resolution, you have to go for CT scan. You can't be doing X-ray for everything. X-ray from which angle is to be done, a practitioner has to decide that. So inadequate planning and survey design, wrong tool selection, method lacking desired resolution, geology ignored, only single tool used. One of the biggest problem. Don't try to save money on geophysics. Always use combination of tools. Then only you will get unique solution. Technological failures, data processing and interpretation error. One big issue which is coming up lately. In our time, it was all manual interpretation. Today, it's all computerized. You put anything into the software, something beautiful will come out of it. Colored plot, beautiful colored plot. Beautiful, but meaningless, inaccurate. So that's again a big problem, data processing and interpretation errors. So with this, I will conclude my part of presentation that these methods provide valuable and continuous information for planning and execution of tunnel and underground projects. These methods should be used in addition to applied geological and geotechnical exploration to achieve accurate and continuous models of the subsurface in short time schedule. If you want to get maximum benefit out of it, we should have intensive discussion between geologists, engineers, and geophysicists at an early stage of the project. And combination of different methods, that is geophysics, geology, geotechnics, and joint interpretation technique. That is what is essentially important. And it leads to increased safety and decreased risk. And second part of the presentation, as I said, will be taken by Miss Meghna Rawat. Meghna has a master's in geology from Srinagar Garhwal University. She is an engineering geologist with more than 17 years of experience in multifarious projects in infrastructure, tunnels, and ground engineering. She is working with Sequent as customer solution specialist, Leapfrog Works. And with this, I'll invite Meghna to please deliver her presentation. Welcome, Meghna. Floor is all yours now.
Thank you, sir. Thank you so much for the great introduction. First of all, I would like to thank Team Parsons to give me this great opportunity to participate in today's webinar. So this is my first time presenting along with Dr. Sanjay Rana. Thank you, sir. So now I will share my screen and I have prepared a small presentation. So firstly, I would show my presentation and then I will open Leapfrog software where I'll show one case study for a tunnel project. So let's start. Let me share my screen. So can you see my screen?
Yes, sir, that's available.
Yes, Meghna, it is visible.
Okay, thank you so much. So it's a little bit. All right, so first of all, I would just like to, as Sir has already introduced me already. So I'm working with Sequent from last 1.5 years. Previously, I was working with AECOM. And most of my experience includes detailed design consulting for railway tunnels, metro tunnels, and also few hydropower tunnel projects. So so I have more than 17 years of experience, as Dr. Rana has already told. So my role in Sequent is I'm basically a customer solution specialist for Leapfrog Works software. So I based out of Delhi, and so if many of you must have already known about our company Sequent, but some of who there are some people who doesn't know about Sequent. So I would like to give a little background for our company. So Sequent is a Bentley subsurface company. They are software providers, especially for geoscience softwares. The company is headquartered in Christchurch, New Zealand. They are major providers of geological and geophysical modeling software, and they also have solutions for geotechnical stability and cloud services for data management. Their flagship software is Leapfrog Works. So Leapfrog is a dynamic software which works based on fast radio basis functionality, which means it creates the best fit geological surfaces based on the available data. And it also updates the 3D model on its own as and when new data comes in. So that's why it is a dynamic software. So today, I will demonstrate a Leapfrog Works 3D model for a railway tunnel project. This railway tunnel project is in J&K, and it's a part of Jammu-Udhampur rail link. This is tunnel number 25. This data set, which has been used in this project, is provided by Rights Limited. We are highly thankful to them for sharing data with us. So this railway line is already constructed and fully operational. Here we have few sparsely distributed exploratory borehole data available. So total length of this tunnel is 1.2 kilometers. And we have 4 boreholes in this tunnel. 2 are at the portals, so we do not have any information about those boreholes, and 2 are within the tunnel. So over a period of time during the operation of this railway line, Northern Railway have observed few instability drainage issues in some of the tunnels. There was major seepage problem observed in few tunnels, and tunnel number 25 was one of them. Tunnel portal stability issue was also observed at few other tunnels because of very poor rock mass conditions at the portals, especially. So in continuation with technical inspection, hydrological and geophysical studies, an additional set of ERT and SRT was proposed, and that was executed along the tunnel and nearby areas. So RITES wanted to identify major water seepage source within the tunnel and propose an effective grouting scheme to make sure the tunnels are effectively watertight, especially during the monsoon season. To achieve this, they suggested to create a 3D groundwater model in LeapFrogWorks to understand the groundwater network and the typical source of water. So in this model, we have used the ERT data as well as the available borehole data to create a groundwater model. So this is just Jammu-Dhampur rail link as shown in Google Earth image. This is tunnel number 25, which I will be talking about. So this is just a Google Earth plan and profile along tunnel 25. So here we can see initially tunnel is excavated in high overburden, and then later it is under a shallow overburden. So this image is from just a Google image, a Google Earth image, which shows one of the ERT acquisition. The ERT is just electrical resistivity tomography. So this, the collected ERT data was processed and inverted using REST-2D inverse software, and was also gridded in OSIS montage. So it means that we have got the point data from REST-2D inverse from the raw data we have inverted in REST-2D, and then we could also arrange the grids in OSIS montage. After processing and inversion, interpretation was performed based on the local geological knowledge, which can then load into LeapFrog to generate a 3D model for better visualization. So here in this slide, image 1 shows an ERT data imported as point data consisting of XYZ coordinates and a resistivity attribute. So on left-hand side, we have this image, which shows the point data. And on the right-hand side, the same point, the same data set has been gridded in OSIS montage. And then we could get some grids out of that data. So there is a difference between the point data and the grids. So the point data will give you the information only on those points where the locations are available. On the other hand, grids will give you the entire data. It will interpolate the information for the entire region, and it will give you the grids, proper grids formation. So this is the difference between the point data and the grids. So if you can create the grid and get some grid information for your resistivity data or your geophysical data, then that would be a very good source of information through which you can create a accurate groundwater model or ground model. So below the third image is the overlay interpretation. So interpretation was done on knowledge of resistivity and geology of the area. So here we can see the point data as well as the grids are overlaid together. And here you can see the difference. So we have, for grids, we have information for throughout the area. But for the point data, we only have a scattered information wherever we have the point sets. So this was like few more ERT lines were there, which were proposed parallel to the tunnel alignment and also along tunnel parallel to each other along the alignment. So this was the a lot of some good amount of data was available. And using LeapFrog, we can generate a 3D model based on these interpretations. Something like this. So where we have the output volumes generated, which are created from the resistivity values, different interval of resistivity values. Now we have a better understanding of the area of interest to investigate water seepage and other instabilities. So with the help of this data, we can also propose some additional investigations wherever we think that we have a water saturated areas, or we have more seepage. So we can propose some additional borehole investigation along with the geophysical survey. So this was the end of my slide. Now I will quickly go to Leapfrog Works. So is it okay? Am I audible or not?
Yeah, you're audible, Meghna, but your screen is black right now. We are not able to see your screen.
I think I need to share again.
Yeah, I think you have to share the screen. You must have shared a window earlier.
Yeah, maybe. Okay. Let me check again. Please move. Screen.
We can see your cursor, nothing but the cursor.
Okay. Let me share again. Share. Please move this interface from the shared application. Is now visible?
No, Meghna.
No.
I think you stop sharing once. Till now, you have not stopped sharing even once. Just stop sharing your screen. I'll tell you when it stops.
Share settings. Stop. I have multiple windows right now.
No, first of all, stop sharing your screen. Your screen is still shared.
Okay.
There will be some icon there, stop sharing. So just stop sharing your screen first. Yeah. Now go to share and share the entire screen instead of any window. And then you can go to that your Leapfrog window.
Okay. So I hope now my screen is visible.
No, your screen is, yeah, now it is starting.
Okay.
Yeah,
So,
got it. Now it's Leapfrog. Perfect. Okay.
Thank you so much, Dr. Sanjay.
Yeah.
All right. So now I will show this data set into Leapfrog. Okay. So now I'm opening Leapfrog Works. This mouse is giving a lot of trouble actually. So now I have opened my Leapfrog software. This is the user interface of this software. This is our 3D scene, which is I have XYZ coordinates here. And on the left-hand side, we have project tree. So from where we import all the datas. So firstly, I have already imported all my data here on the left-hand side. I just have to drag and drop it into the 3D scene in order to visualize that. So I have imported the available boreholes in the area. So I will just quickly go to the borehole data folder and I will import my boreholes. So here we can see I have this for tunnel 25, we have these 4 boreholes. So these 2 boreholes, we have some data, but the other boreholes, we didn't add some data because they were at the outside the portal. So right now these 2 boreholes are there. And I have this legend as well. So if I click on this legend, so I can see I have this sand rock. And in between, I have some silty clay stone, and then again sand rock. So these are the boreholes. Then I have also brought in tunnel 25 alignment. So I'll quickly go and bring my tunnel 25 alignment. So this is my tunnel. This is just a line, a GIS line. Then I will also drag my DTM. digital terrain model, so which is a drone imagery in this case, and we have imported here as a DTM. So I'll go to my mesh folder and I will bring my digital terrain model. So this is the drone imagery for this particular area. So we can import different kind of DTM or DSM or digital elevation model or any kind of point data to create a mesh or to create a surface. And then that surface can be utilized as a topography. So this is the DTM for this particular tunnel. So now we can see how sparsely the boreholes are distributed. Just 2 boreholes for this 1.2 kilometer tunnel. So now, as a part of additional investigation, some ERT data acquisition was carried out. So now I will bring this ERT data as point data. So what I will do, I will quickly just switch off my boreholes, and then I will go to my points folder and I will import my my resistivity ERT data sets. Now I will switch off my DTM. So this is the data set. So these were all the data which were provided by the by rights. So these are, if I just bring all those by pressing Control and selecting all of them together, and bring the data here. Yeah, so grid has been imported to Leapfrog as from OSIS montage. That's correct. So this was the raw data. This was just the .dat files. So this data has to be inverted in Res2D inverse. Then we could get the XYZ coordinates as well as the resistivity values in one file. So earlier we had just elevations, we have chainages. So in that raw files, so then we have to invert the data in Res2D inverse, and then we can get this inverted files. And the grids we can get from the OSIS montage software. So student version, I think we don't provide for the softwares, but we can give you trial for 15 days. If anybody wants to try the softwares, we can always share the license, the trial license for 15 days.
Meghna, sorry for interruption. We can take the questions later. Don't worry about the questions right now.
Okay. Because I have a habit to answer the questions.
I know. We'll take it later. Don't worry.
Okay. Thank you, sir. So this is these are all the point data sets. So these points symbolize ERT data imported as points containing consisting of X, Y, Z coordinates and a resistivity attribute. So for example, if I just switch off all of them and just switch just one, okay. So here, for example, if I just zoom in, if I click here, so I can see this is X, Y, Z values for this particular point. And this is the resistivity value, 107, this green color. And I also have the legend. So once we import this data in Leapfrog, we can get this kind of data. So if I press on this blue point, so this is my XYZ and 25 is my resistivity value. So right now I will click on all the my point data, and then I will select the resistivity value. So now these are the resistivity value actually. So these colorful, you can see on the right hand side, top right corner, we have resistivity index. So here from 1 to 500, we have the resistivity values. And the bluish ones are the one which are very lowest values. And the red one are the one which are the highest values, means there is hard rock or good rock mass. And all this blue color areas are all where we could have some water saturated zones or some clayey, gougy material, rock strata. So different litho units are interpreted based on the resistivity values. So what we have done is, based on the final geophysical report provided by RITES, low range values correspond to highly saturated free flow zones or clayey material. Intermediate values, resistivity values, correspond to highly saturated weathered zone. Higher range values correspond to unsaturated intermixed with rock. So that was the interpretation from the report, which we interpreted. And then we could create a formula in Leapfrog Works. Once we have imported this, then we can create, categorize our numeric data into a category. So here, for example, what we have done is, we've just divided the resistivity value in 3 intervals. So if the resistivity is less than or equals to 10, then the category will be free flow. If the resistivity is between 10 to 80, this will be highly saturated weathered rock mass. And if it is 80 to 150, it means that is gravel, pebble, cobbles in sinter-silting matrix. Otherwise, it will be unsaturated if it is greater than 150. So once we have set up these calculations, so then we can change this numeric data into a category information. So then we can just go as per the calculation, and then we have created the saturated and unsaturated categories out of the resistivity values. So now, once I've done this, I can create a 3D geological model, constraining my model within the available data. So based on this data, I have created a geological model here. And this is my model. So if I drag and drop it, I've already created the model. So I can see that if I press D, enter, and home. So based on these ERT data along the alignment, we could create the output volumes. Firstly, we need to generate the surfaces. And once we have the surfaces, then we can create the output volumes here. So these are the volumes. And if I have opened my legend, so I can see that this purplish is the unsaturated zone. The blue one is the free flow, and otherwise this is all other is intermediate. So free flow, unsaturated, and intermediate. So we have divided our area into 3 different zones. So if I bring my topography now, this one, so then I can see that I have some water or some small nalas which are flowing over my tunnel. So this one, here we have this nala here. If I see carefully, we can identify a few major nalas flowing over the tunnel. I can quickly digitize them and correlate with my model and ERT lines. I can check whether there is any connection of this water stream into my tunnel. So I've created this polylines here. And if I drag and drop, so I can see this is the nala. And then I have created this mesh. So this is a mesh, which is just the groundwater table, water line. And now if I cut a section across this, So I will just press D just to view from the top. And from this slicer, I can just cut the section across. So then I can see that wherever I have this nala cutting, there we have this saturated zone, which is like upheaval kind of thing. So it is on the top, the water level is very near to the surface. So, and this ERT profile is also giving the same information, which is this one. So these are also highly saturated zones, which is also cross-checked by the ERT profiles. So we can check and we can cross-check our ERT data with the help of any topographical features we have. So here we can see we have this water table going upward. So it must have definitely related with this nala, which is flowing here and which is coming right across our tunnel. So this is our tunnel. And if I just quickly bring my tunnel here, polyline tunnel sliced. So this is my tunnel. So we can see the tunnel is water saturated wherever we have this dark blue. So it means there is very low resistivity values. And then here we might get a lot of water seepage when we are during monsoon season especially. So also once we have created our 3D model, then what we can do is we can create a combined model, and then we could also understand this one. And I will switch off this model and also my resistivity values. So once I have created my combined model can be created very easily with the help of geological model and the tunnel radius. So then I can also bring the total volumes of the total volume of the free flow area and also total volume for intermediate zones. So like this, if I press here, so this is 54,920 cubic meters. So which is a saturated area. Similarly here, I can see that my tunnel is so here I can see that in the entire tunnel, wherever how much total volume of free flow area from where to where and what is the total volume. So in this way, we can also plan our grouting scheme and how much quantity of grout will be required, and which are those places where we need the grouting especially. So this kind of combined model we can obviously create once we have our 3D model. So here I will switch on my TDEM again and my profiles and the boreholes. So once we have our topography information, and so we can, we can also always recommend where do we need some additional investigation. For example, here I have this nala flowing up. So we can drill one more hole here and then one more borehole here somewhere at these two locations, so that we can understand what is the depth of groundwater table, and also how much deep the water level is there exactly, accurate. So in this manner, we can propose our additional investigations. So that was about the 3D model and the combined. So that was it from my side. So if there are any questions, then I'll take them later on.
Sure.
Thank you.
Thank you, Meghna. Thank you so much for this wonderful presentation. I think everyone could see the value of putting life into the data, and then seeing it together with the geotechnical information or with the image which you had, and ultimately taking valuable decisions based on that, including additional investigation if required, doing the calculations that if we are going through this tunnel, what kind of formations, what kind of volume we are going to come across. So wonderful presentation. Thank you so very much. And now I'll quickly take questions because we are already 4:22. So I'll very quickly take questions. But remember, I and Meghna both are available on our email. So whatever question comes to your mind today, tomorrow, or 10 years from now, please feel free to contact us on the email. And my email ID will be put by the team there in the chat box. Meghna also can just put the email ID in the chat box, and please feel free to connect. Now, quickly, the first question is, will well logs help in detecting the anomalies between the boreholes? It's from Siddharth Parasar. So Siddharth, well logging, when we talk about, well logging is about getting the information from the well log, all right, about the formation which is surrounding it, right? It is not something which gives you information between the boreholes. If you need information between the boreholes, you can do tomography between the boreholes. That can be P-wave tomography, that can be radar tomography also. So tomography is something which is done between the borehole, and well logging gives information around the borehole, what the formation you are encountering, all right? Then Hemchandra Upreti is asking, due to space constraint, geophysical work not carried out in metro city, can this heliborne work in metro projects? So, Mr. Upreti, as I said, I think I just listed three limitations of heliborne, and one of them was it is not used in the urban areas. Okay. If you want to work in the urban areas, there are methods which can be used, geophysical methods which can be used in urban area. You can, if the area is very noisy, you can use noise-based methods. So you can use things like MASW or REMI, which are noise-based and can give you valuable information. You can use ERI, it is not affected by noise unless there are a lot of metallic objects where you're investigating. You can also use tomography, which I talked about, so between the boreholes to get a very good idea of your metro corridor. GPR is always used in the metro project to detect underground utilities and things like this. So not the heliborne for sure, but there are a suite of methods for metro project. Maybe we can do just one webinar for metro. Then third question again from Mr. Upreti is, what is the minimum distance one hole to another hole in seismic refraction or reflection? I don't know what you want to understand. Reflection, if you're talking about, generally the hole-to-hole distance for short hole, what we talk about can be 10 to 20 meters. That's why I say reflection becomes logistically very challenging, especially in the hilly areas. Mr. Beeman Day is asking, does the passive seismic sensor is deployed one at a time or multiple sensors connected to one another for one data set for analyzing the data? Mr. Day, in passive seismic, we are putting a number of these sensors together. They all are synchronized by GPS, so their timing is synchronized. They are 24 hours continuously reading seismographs. So 3 component sensors. So we are recording all the activity 24 hours in 3 directions, right? So that is 3 components, so to say. And they are all synchronized by GPS, and we put number of them together. So recently we are working on a project in Assam, and there we have put 400 of these sensors together, right? So number of sensors, it's not one at a time. All right. Then Mr. Tong Hang Seng is asking, what is the maximum distance between 2 boreholes for tomography testing? Well, as I showed you the example, the maximum distance in this particular case went up to 115 meters. But for this kind of distance, we use explosive source, right? If you're using a source like Sparker, generally in soils, 30 to 40 meters is recommended. If it is rock or very competent kind of a soil, can be slightly more also. But that is what we recommend, not more than that, because then the energy becomes very weak by the time it reaches the receivers. Then Mr. Rasanayam is asking, under building will not affected by building piles. This question is not complete. So under building, when we are doing tomography, what we are suggesting is, let's say there's a row of building and you need information under that because your metro corridor is passing under that. In that case, you can do a borehole in the front road, one borehole in the service lane, and then do the investigation. If the piles are coming in between, that's not a problem. These are just, a high velocity object which will be mapped in the tomography. It is coming in the plane, so it is not a problem. All right. Then Mr. Siba Shankar Gowda, sir, could you suggest a suitable method to detect the exact depth of pile foundation below existing building to confirm the infringement into the tunnel section underneath to a proposed metro rail tunnel? There are, couple of methods which can be used to understand the pile foundation. One is parallel seismic. So parallel seismic is one method which can be used. Even tomography is something which can be used to detect the depth of the pile foundation. So since this particular presentation is not exactly on pile foundation, but you can write to me and I'll send you details of these methods. But parallel seismic and cross-hole tomography, these are two strong methods for pile foundation depth. Mr. Hemchandra Upreti, which software basically you are providing? I don't know what is this question and for whom this question is. There is, as far as we are concerned, there is no particular software I have talked about in my presentation. It was software is just one part of the entire flow. We have talked of different methods. When we talk about Meghna's presentation, she was presenting Leapfrog as a software. Mr. Shashank Pai is asking, it would be great to understand geophysics integration into Leapfrog without Oasis montage grids. Meghna, for this, I would like you to please come in. This question.
Yeah, thank you, sir. So yeah, without OSS montage also we can import the data into Leapfrog as a point data. But if we need the grids, so then we need OSS montage. That is the.
Thank you, Meghna. And next question again is for you. Is Leapfrog paid software or student version is possible?
I will come back to this question later. I need to check with my team. I'm not very much sure about it.
Next question again is for you. Is the grid imported to Leapfrog from Oasis Montage 2D or 3D?
It's Oasis montage, simply. So it's not 2D, 3D, it's just Oasis montage.
Dr. Dinesh Gupta is saying maximum depth of penetration in these case studies. So Dr. Gupta, different methods have different depth of penetration, all right? So as we said, starting from heliborne time domain electromagnetic, we are talking of 600 to 800 meters, depending on the ground conductivity. Passive seismic tomography, practically there is no limit of depth because wherever the earthquakes are coming from, these waves are illuminating the entire, area between where the earthquake is originating from and the top. So, like as I said, in oil and gas industry, we are going up to tens of kilometers in case of passive seismic tomography. Seismic refraction, I indicated 70, 80 meters without 60, 70 meters rather without explosive. With explosive, we can go much deeper. More power of explosive. But generally we keep seismic refraction limited to 100, 150 meters. Electrical resistivity imaging, you can go up to around 300 meters, 300, 400 meters. So depending on the length of your array, etc. So different methods, different depth of penetration. GPR definitely tens of meters only. So many people, for every problem they want to solve using GPR. As I said, I introduced GPR in the country in '96. And today I'm the person who says that GPR is not geophysics. GPR is one of the very strong tool for shallow subsurface investigation. So let's be very careful about what we are choosing. Mr. Hemchandra Upreti, simply please let us know which data you require to run this software. Mr. Upreti, this is Megha, this is for you.
So simply we can have, if you have borehole in details, borehole drilling, exploratory boreholes in your project area. So we need just the CSV files for the coordinates as well as for the lithology. So that is the only two major files which should be in CSV format. If you have those files, you can import your borehole data.
Thank you, Meghna. Then Mr. Arjun Singh is asking, do you provide practical training on data interpretation? So, as a geophysicist, I also contribute towards education. So there is an academy which is called AF Academy, and there is afacademy.org. That is a website. Rashik ji can put it in the chat box, afacademy.org. There are various courses there, including electrical resistivity, seismic refraction, MASW, GPR, etc. And these courses cover the entire aspect of these methods, including basic principle, data acquisition, data processing, and interpretation. So you can go to this academy, and it has been posted right now in the chat box. You can go there and look at these courses. Mr. Vijay Singh is saying, are you saying that as ERT values go up, the rock condition improves? Yes.
Yes.
Good rocks, dry rocks will have high resistivity. As soon as the moisture or water ingress takes place or weathering takes place, resistivity goes down. So yes, that's exactly what we are saying. Mr. Shashank Pai, why is the saturation zone localized? Shouldn't it run across the entire Nala? This is for you, Meghna.
So actually, it is not it's just the saturation zones and the areas where we have some water in the pore spaces of the soil. So they might be localized as well. It's not necessary that they should flow like a river. So that's why they are localized, because in geology, it's highly unpredictable, as we all know. It's never like a cake, So it's pretty unpredictable. We never expect geology to be same in the entire place. So it might differ. Yeah, thank you.
Next question is also for you, Meghna. Is it possible to estimate or identify the water quality and flow direction using this software? This is coming from Mr. Manoj Kumar Dangwal.
Water quality we cannot identify.
Water quantity, I'm sorry.
Water quantity, yeah, quantity we can identify with the help of our output volumes. So we can, of course, calculate the total volume for the saturated zones. Thank you.
And flow directions?
Flow directions also we can identify. We can create the contour, groundwater contours, and then we can identify where the water table is going, whether it is going below or whether it is rising, like that. So we can do that in Leapfrog.
All right. The next question again is from Mr. Manoj Kumar Dangwal for you, Meghna. Is it possible to estimate or identify the water quantity and flow direction using this software? This you have answered already. Can we also identify the purged water table and the permanent water table using this software?
Yeah, we can identify the purged water table, but we need the groundwater data for if it is a time-dependent data, that would be more useful.
Next question is from Johani. Thank you for such a presentation. Just curious, is there any specific features for such an analysis of geophysical data in Leapfrog work that we don't have in Leapfrog Geo?
No, there is nothing like that. We have all the features same to same. Whatever we have, all the folders and functions in Leapfrog work, same are also provided in Leapfrog Geo. So there is no change.
Next question is from Tarun Chandra. Good afternoon, Dr. Rana and Ms. Rawat ma'am. Thank you for a wonderful and insightful session. I want to ask you that a third year BSc Geology honors student at UPES, I'm very eager to bridge the gap between academics and industry. That's a very noble thought. What specific skills or software should we focus on right now to build our practical knowledge? And how can students best secure hands-on field projects or internship in engineering geophysics? So part of it I'll answer. So if you're interested in any internship, we do take interns in our organization. You're more than welcome. And once you're here, you will be exposed to field work in the field of engineering geophysics, data processing, and different software which are required for data processing. Leapfrog part of internship, Meghna will be answering.
Yeah, so actually, we provide trainings to our clients, regular trainings, and one part of our job is to give trainings. But my colleague Arghya Kamal is also joined. So Arghya Kamal, can you answer this question? Arghya Kamal, are you there?
He or she might not be able to unmute herself because there are restrictions on this thing. No problem. He or she can just type it on the internship is part of the Bentley's education. Great. He has answered in the chat.
Yes.
So yeah, you can always write to Bentley's for this. Okay. Next question is from Sabin Tiwari. For a city like Kathmandu, the area is lacustrine deposit with black cotton clay. And if we plan for underground metal project, how can we proceed and what geophysical constraints will be there? And how can geophysics Help us there. Can we build metro underground in such geology? Wow. Now that's almost a consultancy question. I can take it as a consultant. I would love to. So how geophysics can help you is to understand your underground better. And without understanding your underground and geology, I really cannot answer this question whether a metro project is possible or not. All I can say is that the way engineering has really developed, most of the geologies we are able to do underground works. The only thing is you should understand your underground in the best possible manner, and where we as geophysicists or geologists come in picture. Next is Ahmed Sabir. What are the limitations of different geophysical methods, target depth in the presence of shallow groundwater? So I just answered about the depth part of it. When it comes to seismic method, groundwater is not of much significance. Of course, PV velocity goes high when it comes to groundwater, but otherwise there is no problem. In electrical methods also, till the time the groundwater is not very conductive, we are able to see under the groundwater. So with the shallow groundwater, we are working with all the geophysical methods practically. Mr. Karma Lore is asking to Rawat ma'am, can we also use structural data like dip and dip direction, which we obtain from surface outcrop mapping to develop the geological map? In detail, I will contact you through mail. Meghna ji.
Sir, so yeah, the answer would be yes, we can import the structural data into Leapfrog as CSV files. So we can also import geological mapping and create geological surfaces out of that mapping data. We can very much do that. Yes, that is what we do daily, actually. I have also write the answer, actually.
Yeah, okay, great. Next is Johani again. We often work with large sets of different methods for our geophysicists on deep mining projects. I wonder if any accessible tools have emerged for semi-automated correlation and analysis of all the data. So, Meghna?
I'm sorry, sir. Can you repeat?
Not a problem. So, Johani, as you saw, there are these software suites where you can put different data, because I have also some exposure with these tools like Leapfrog itself, where in a project we had put the seismic and resistivity data together. And once you do that, you can do different kind of computations and analysis. So that's almost semi-automatic, but it's possible. Revati Raman, can geophysical investigation assist in identifying the most suitable location for gravity dam foundation along a river valley? So, Mr. Raman, yes. These methods are very, very suitable for your site investigation to choose the right location. So you do the investigation along the dam axis, along a few alternative dam axes, look at the features there, look at the depth of the bedrock, look at the presence of shear zones or fault zones, etc. And based on that, you choose the method. So it is absolutely useful for gravity dam foundation along a river valley. Mr. Karma again, for quick, cost-effective, and high accuracy in mountainous terrains, which geophysical method will be suitable? So, Mr. Karma, no quick answers to this question. It completely depends on what is your objective, what is your depth of investigation, for what you are doing the investigation for. I've been working for hydropower projects in mountainous regions since 2001. And I have used, methods like electrical resistivity imaging, seismic refraction, MASW, refraction microtremor for these kind of terrains, mountainous terrains with very high accuracy, quick and cost effective. So depends on your objective. My mail ID will be there. Please write to me more about your project details. Would love to help you with this. Siva Sankar Gowda, as the building area is confined, hence there is no scope for borehole for doing parallel seismic on the SRT. Mr. Gowda, your specific problem, I would like to take it offline. So please drop me a mail with your specific problem. Give me the site details, the drawings and the sketches and all that. We surely will come up with some solution. Mr. Yogesh Kumar Ji, hello sir and ma'am. Even though we did the acquisition and also have to process the data very well, how much can we really rely on the quantitative output from the ERT or from the MASW? For example, if the process MASW data VS of 1300 meter per second at a depth of 15 meter, can we rely on this exact value? Well, that's a very interesting question, Mr. Yogesh Kumar. In the beginning of the presentation itself, I said that geophysics is giving you continuous information of a much larger area in a much quicker way. When we are talking of things like velocity of 1300 meter per second, So if it is 1300 meter per second, if you are asking me whether it can be 1250 or 1350, my answer will be sure it can be. Because ultimately, all these methods are working on the principle of measuring a particular response, then putting the data through a process, in which case it is inversion. Let's say in MASW, you make the Rayleigh dispersion curve, do the inversion, etc., etc. There might be a slight mismatch in that. But from the engineering perspective, what is your requirement of understanding that particular zone? MASW and the methods like this have been proven across the world to be more than just accurate to serve that purpose. Okay. Do not compare them with your borehole methods. As I said, borehole or drilling methods are the most accurate. So once you are getting a drilling information of a discrete point, there is nothing more accurate than that. But that is only of that particular point. So once you put geophysics with your drilling data, that's where the strength comes from. Okay. Mr. Saurav Upadhyay, Tunnel 25, when it was observed regarding issues of water seepage, can I assume that these tunnel feasibility and planning stage were not carried out, as I understand these issues cropping post-tunnel construction? Also, any other study done in addition to ERT at Tunnel 25 or any comparison? Meghna, for you.
Yes, sir.
This question was for you. Tunnel 25, when it was observed regarding issues for water seepage, can I assume that these tunnel feasibility and planning stage were not carried out, as I understand these issues cropping post-tunnel construction? Also, any other study done in addition to ERT at Tunnel 25 and any comparison?
Any other study, I would say boreholes were done initially, and there might be some other previously done geophysical surveys, but I will contact the client for this, and they will get back to us. They can tell better. I don't have much information.
Okay, another question for you is how the depth of the model in Leapfrog is decided. Is it the depth of drill hole depth and inverted ERT or SRT depth?
So yeah, it is basically both of them. So whatever is the deeper information we have, we will take the depth for that particular investigation.
Next question is Mr. Saurabh. This beam data is acquired with TBM. Yes, beam data is acquired with TBM. As the TBM is moving stroke by stroke, the new data is being collected. You don't need to stop the TBM at all, and this is done with TBM. Okay, there are lots of questions, so I'll now have to skip few questions, and please write us on the mail. I'll just take questions which can be important for everyone. Okay, all right. Okay, I'll not take specific questions now because there are more than 31 questions yet to be replied. So, all right. Okay, Meghna, it's for you. From Ankit, could you please suggest which software would be more suitable between Oasis Montage and Leapfrog for integrating ERT, SAR, and geospatial dataset to generate and final output for hill slope stability analysis?
Yeah. So, sir, I have already answered actually in the chat box.
Okay, great.
Yeah, already answered.
Great, fine. So I think we will have to stop it here because it's already 4:45. I'm sorry we are a little late in winding it up. Thanks for all your questions. And now I'll request Rashik ji to allow everyone to open their videos so we all can come on a single screen. We can take some screenshot of this beautiful afternoon we had together, afternoon or morning or evening, depending on which country you're joining from. And you can unfocus me also. Yeah, that's great. And by the way, we had around 1,070 registrations from 82 countries in this webinar. So I'm very, very happy to see all of you. It's absolutely a pleasure. And now Anushka ji will take the screenshots of us. Anushka, you have to scroll through various screens because not everyone is fitting in one screen. There are 8 screens right now where all the faces are there. Yeah, I can see it's 1 to 8 or 1 of 8 only. And once you have finished it, just let us know because then we'll close the webinar.
Well, I just need 2 minutes to scroll down and I'll let you know.
Thank you, Anushka. And why your video is not on, Anushka?
Actually, I'm not at home right now.
Okay, all right, no problem. You're caught. Thank you. Thank you. It's always a pleasure to conduct these webinars because it really enables us to talk to each other. And although we are not able to do two-way communication because of the number of participants, but believe all I can assure you is that we are always there. Our email IDs are already with you. On behalf of Meghna, also, I'm making this promise that whatever question you have regarding anything, just write to us. My response time is 24 hours maximum. Meghna, you like to make some promise on that?
Yeah. No, not as of now, but yeah. They can always share the questions, and we will get back to them.
Absolutely.
Kamal has already taken a note. So, and sir, also one more thing, can we get the email IDs for all the participants, if possible, so that we can contact them for future?
Sure.
Thank you, sir.
Anushka is done. All right. So with this, it's time to say thank you very much for being with us for last 1 hour 47 minutes. Actually, pretty long, but thank you. Has been a pleasure.
Thank you so much, sir.
Thank you, sir.
Thank you.
So much.
Thank you.
Thank you very much, sir.
Thanks a lot
Thank
for
you very
being
much,
with.
sir.
Yeah, thank you.
Thank you. Thank you.
Thank you very much, sir.
Thank you, sir. Thank you very much,
Thank
sir.
you. Thank
Thank
you,
you,
sir.
sir.
Thank you so much, sir.
Thank you a lot.
Thank you very much.
Thank you so much for the wonderful presentation and opportunity given to us.
Thank you for being with us. Thank you.